MACHHOLZ, and you are listening to Looking Up with Don. This is the Looking Up with Don podcast, episode number 46 for the week of November 18th, 2020. The related website for this podcast is donmachholz.com. That is spelled DONMACHHOLZ.com, 2 H's. What's up in the sky this week? As our week begins on Wednesday, November 18th, the moon is a crescent in our evening sky. It will reach first quarter on Sunday, November 22nd, and by next Tuesday, the moon will be 70% full in our evening sky. This is a good week to not just look at the moon, but study it and learn some features. On November 18th and 19th, the moon passes south of Jupiter and Saturn. On the evening of Wednesday, November 18th, the Western Hemisphere will see the moon approaching Jupiter from the west. The moon will be closest to the western horizon. Jupiter will be above the moon, and Saturn will be above both. And again, that's for the Western Hemisphere on the evening of Wednesday, November 18th. A few hours later, on the evening of Thursday, November 19th, as we cross the date line, the Western Pacific and Eastern Asia will see the moon centered below and between Saturn and Jupiter. Around that time, the moon passes over Comet MACHHOLZ, but it is unlikely the comet will be visible at 9th magnitude. You might also want to use the moon on Wednesday, November 18th to find the planets Jupiter and Saturn in the daytime. First find the moon, then Jupiter, which is north and east of the moon by several degrees. The amount depends upon when you look. Jupiter should be visible in the main scope and may even be visible in the finder scope. From Jupiter to get to Saturn, go 0.7 degrees north and 3.4 degrees east. Or use your go-to telescope, which will find it for you automatically. Next Wednesday, November 25th, the moon will pass south of the bright planet Mars. If you were on Mars, you would see our moon passing just south of the Earth. You might want to find Mars during the daytime using the moon as a starting point next Wednesday, November 25th. We still have the Leonids meteor shower in the morning sky. The peak was Monday, November 16th and Tuesday, November 17th, but you can still see some of the meteors from that shower. Venus is low in the eastern sky at dawn and Mercury even lower in the sky. With the COVID virus still prominent enough to continue social distancing, most local astronomy clubs continue to hold their meetings via Zoom, Facebook, and/or YouTube. As I have done in the past on this podcast, I again encourage you to scan the internet for club meetings which feature guest lecturers who are presenting subjects that might be of interest to you. Or maybe a talk about something you know next to nothing about that you want to learn more. Contact the club and ask to be invited. Most will allow non-members to sign in and participate. Will you be able to see the International Space Station this week, which for our purposes begins Wednesday, November 18th through Tuesday, November 24th? It all depends upon your latitude. This week we have 7 zones. All you need to know is your latitude. For those living around 65 degrees north of the equator, the ISS will not be visible this week. Next week, nor for several months. That is around 65 degrees north. From 54 through 60 degrees north, The ISS will be in your evening sky, but not at the beginning of the week. Start looking for it this weekend. From 30 to 54 degrees north, the ISS will be in your evening sky for the whole week. From 15 through 30 degrees north, the ISS will be in your evening sky, but not for the whole week, just the first few days of the week. In the equatorial region, from 15 degrees north to 25 degrees south, the ISS will be in your morning sky, but only for the first few days of this week. Heading further south from 25 to about 40 degrees south, the ISS will be in your morning sky, but only for the second part of the week. And south of 40 degrees south, you won't see the International Space Station at all this week. To determine where it will be in your sky, go to the website heavens-above.com and enter your location, then click on ISS. I have been reviewing a book I wrote and published in 1985 entitled A Decade of Comets. It is a study of the 33 comets visually discovered from 1975 through 1984. The series began in podcast 34. The book has 6 parts. And this week we finish up part 6, the orbital elements. The book is free on my website in sections. The first part can be downloaded in podcast 34. Then sections are downloadable each week since then. This week, download podcast 46, A Decade of Comets, part 6. If you downloaded part 6 last week as part of podcast 45, there's no need to do so again because they are identical. This week we pick up at figure 37 on page 102. I examined the ecliptic latitudes of the comet at discovery. This is different than the declination of the comets at discovery, which was briefly discussed in part 4, page 82. But the ecliptic latitude tells us if a comet was found above or below the plane of the Earth's orbit around the Sun. We find we have a bunching up of comets found just south of the ecliptic from 0 through minus 40 degrees. And we find a bias for morning comets to be found south of the ecliptic and evening comets to be found north of the ecliptic. That morning versus evening imbalance is similar to the declination imbalance. That morning comets were found generally south of the celestial equator, and evening comets were found north of the celestial equator. But a look at the 94 comets found since the beginning of 1975, not just the 33 found in that first decade, but the 61 found since then, shows no such imbalance for declination for morning and evening discoveries. I haven't run the study of 94 comets for ecliptic latitude, but for declination, the north-south and the morning-evening sky are generally balanced. They have said for years that periodic comets are generally found near the ecliptic, and long-period comets are found far from the ecliptic. That has been oft repeated in comet circles because periodic comets, those that return in under 200 years, have orbits of low inclination. They hug the same plane as the Earth when going around the Sun. So, since they travel within a few degrees of the ecliptic, then where the ecliptic runs through the sky, that is where to find them. The large search surveys cover the ecliptic very well and find lots of asteroids and comets in this region. Why is this? Let's assume that originally all comets come from all directions. Those with low inclinations would have the greatest chance of being influenced by Jupiter, and have their orbit shaped into that of a periodic comet. Additionally, some comets coming in from other directions, from above or below our solar system, some of them also have a chance of being influenced by Jupiter, and then in time, from what I understand, those comets' orbital inclinations, after perhaps many trips around the Sun, level out to an inclination similar to our own. How about those 5 short period comets, that is, they come back in under 200 years, that were discovered in our decade of comets? Table 19 shows that most of them were found near the ecliptic. Table 20 shows that 8 of the 33 comets found during this decade will return, with orbital periods of 5.96 years to 446 years. The shorter period comets have low inclination orbits, as discussed, but the 4 longer period comets have higher inclinations, including 2 which orbit the Sun in the opposite direction that we go. Next, I show the 6 comets that during the decade have hyperbolic orbits. These seem to indicate they will never come back. Here's the next question that I examined in this book. How far from the Sun are comets at discovery? Figure 38 shows the distance of the comet from the Sun at discovery. The range is 0.5 AU through 3.3 AU, with AU meaning astronomical unit. The average distance from the Earth to the Sun, which is 93 million miles and 150 million kilometers. Almost all comets are found within 2 AUs, and most of them within the orbit of Mars, which is 1.5 AU. The average is 1.24 AU for all 33 comets, with morning sky discoveries being slightly closer than evening sky discoveries. This is probably due to the faster brightening of comets in the morning sky, as we generally are approaching them in the morning sky and receding from them in the evening sky. How close are these comets to the Earth when they are found? The range shown in figure 39 is 0.2 through 3.5 astronomical units. This distance often affects how large the comet will appear in the telescope and how fast it will move across the sky. The absolute magnitude of a comet is how bright it would be if positioned 1 astronomical unit from the Sun and 1 astronomical unit from the Earth. Since comets don't normally find themselves in this position, we use formulas to calculate it. The smaller the magnitude, the brighter the comet. Our range for absolute magnitude is from 0 magnitude, that was a bright comet found by Meyer in 1978, to 13th magnitude for periodic comet Denning-Fujikawa, a comet whose brightness has varied over the decades. The average for all 33 comets is an absolute magnitude of 8.54. Another factor in the formula for comet brightness is the N factor. How much does a comet brighten as it nears the Sun? The number is of logarithmic scale, and the average number is assumed to be 4.0. That is used unless the comet's behavior shows it to be something other than 4. A comet with an N of 4 will get 16 times brighter as it halves its distance to the Sun. A higher number means it is a very brisk and active comet. A lower number means it is sleepy, not very active. For 22 of the 33 comets, I use the assumed value of 4 for the comet. For the 11 remaining comets, I calculated the N value based upon the observed brightness over the course of several months. For those 11, the average N value was 4.35, slightly more brisk than the average comet. That is shown on figure 42. Next, we look at the Holeshik angle. In the late 1800s, J. Holeshik determined that when a comet comes to perihelion, that is, when it's at its brightest on the opposite side of the sun from us, it is less likely to be discovered. Dr. Everhart studied this, so did I. And the tendency is true, that comets that come to perihelion on our side of the sun, with this angle being near zero, are more likely to be discovered than those that come to perihelion on the far side of the sun, which in our table is 180 degrees. So one wonders how many comets did we miss because they came to perihelion on the other side of the sun. I end the book with two final tables. One table of the 20 comets found in the morning sky, and one table for the 13 comets found in the evening sky. Each table has the comet's orbital elements, the Holeshik angle, the probability of discovery using Dr. Edgar Everhart's formula, and then my formula. Then I include the number of days the comet spent within 1 astronomical unit of the sun and 2 astronomical units of the sun. Also, I include in this table the absolute magnitude and the n value of each comet. Let's talk about the number of days the comet spent within 1 and 2 astronomical units of the sun. I wrote a basic program that I no longer have the capacity to run, which determined that for each comet. The closer the comet goes to the sun, the faster it travels through space. But the more ground it has to cover to reach perihelion. So, as we are counting the days, we start the timer when the comet crosses 1 astronomical unit headed towards the sun. When the comet reaches perihelion, it is as close to the sun as it will get, and we are halfway to our goal of counting the time it is within 1 astronomical unit, because it still has to come back out. We stop the timer when the comet reaches 1 astronomical unit going away from the sun. Notice a lot of comets spend about 70 days within 1 astronomical unit, with the maximum being 78 days. Now, let's see how long a comet is within 2 astronomical units of the sun. Same thing, but twice as far out. A lot of 200 plus days. By the way, I believe the 280 days for 1978J is a mistype. It should probably be 218 days. Anyway, it takes these comets about 100 days to come to perihelion and 100 days to get back out again to 2 astronomical units. Here is a key point. Almost all comets were found within 2 astronomical units from the sun. So from that distance to perihelion, these comets have about 100 days of travel before they reach their brightest. That is a lot of time to find a new comet, but then there is a lot of sky to cover. I end the book with my musings, and some of it is worth repeating here word for word. As I look at it now, really, it isn't half bad. So here it is, the last paragraph of my book, A Decade of Comets. Quote, "The past decade has seen 33 new comets enter our midst, all found and officially named by amateurs. These intrepid enthusiasts, armed with extensive knowledge of the night sky and warmed by the spirit of discovery, searched and learned to love to search. And somewhere along that long or short road to a comet, the lucky ones realize that there is more to comet discovery than comets. For discovery goes on with every new field full of stars. Who knows what discoveries await us between now and the next comet?" End quote. So concludes the book, A Decade of Comets. I wrote this book, which started as a short study, because after a decade of searching for comets, I had more than 3,300 hours of comet hunting and had found only one comet, and had missed 32 comets. The results found in the book showed me that most comets are found at elongations, that is, the number of degrees a comet is from the Sun as seen from the Earth, of about 45 through 80 degrees. But I was already sweeping that area. I was surprised of the number of comets that I swept over and missed, because they were just a bit too faint. So I continued to work on seeing fainter objects. The result was that I did find the next visually discovered comet on May 27th, 1985. It was magnitude 9.5 and found only 40 degrees from the Sun. No one else visually discovered a comet in 1985. In 1986, I was again the only person to visually discover a comet on May 12th, 1986. Magnitude 10.5 and 39 degrees from the Sun. Maybe everyone else was looking at Halley's Comet rather than comet hunting, or maybe not, I don't know. These two discoveries were bookends to Halley's Comet's visit. The next year, 1987, 7 comets were found visually. I found none of them, and so it goes. From time to time, I've thought of expanding this book, the study of comets, to add 61 additional comets that were found since 1984. That's not likely to happen for several reasons. Number one, I have too many other projects on my plate. Number two, there's no longer a large audience of visual comet hunters seeking this information. 3, what we learn about visual comet discoveries since 1975, well, most of it's no longer applicable in the day of modern surveys. And number 4, others have written well-researched books on comet discoveries. Thank you for being a part of this book club as we have gone through a decade of comets. If you missed any, they begin in podcast 34, and each podcast since then, 34 through this one, 46, has a segment detailing a portion of the book. And the book will continue to be available for free from my website. It was too large to offer it as a full download of the whole book, so you can download it instead in parts. Now for the comets you can see this week. The positions, right ascension and declination of these comets, can be found on podcast 41, Comet Positions. You can also use heavens-above.com to find the comets. For instance, if you're out observing and want to look at one of our brighter comets, go to heavens-above and scroll down to the heading Astronomy, then Comets. Clicking on Comets brings you a list of comets, how bright each is, and whether each is presently above or below your horizon, assuming it knows your location. Clicking on a comet gives you a couple of finder charts in the present coordinates. So you can use heavens-above.com to find comets while out in the field. Comet Howl 88P is magnitude 9.5 and south of both Jupiter and Saturn. The moon passes it on Thursday, November 19th. Evening moonlight makes it difficult to see this comet this week, but it is plotted on podcast 46, map 1. In the morning sky, but rising about midnight, we have Comet 2020 M3 Atlas. It's now north of Orion and shining at magnitude 8. It is still less than 0.4 astronomical units from us, so it appears rather large and diffuse. You can find it plotted on podcast 46, map 2. Finally, Comet 2020 S3 Erasmus is now headed towards morning twilight as it continues to brighten and develop a tail. This is our last moonless week to observe the comet in dark sky, as it rises about 2.5 hours before sunrise. Over the next few weeks, it will get closer to the sun, and it is expected to brighten quite a bit more, becoming a binocular object, possibly even an unaided eye object. The path of Comet Erasmus is plotted on podcast 46, map 2. You have been listening to Looking Up with Don, podcast episode 46 for November 18th, 2020. Once again, the related website for this podcast is donmachholz.com. That is spelled DONMACHHOLZ, 2 H's. You can contact me at dontheastronomer@gmail.com. Once again, that's dontheastronomer@gmail.com. God willing and pod willing, I'll be back next week for another episode of Looking Up with Don. We will discuss what's going on in the sky and highlight some of the specific objects to observe. And we have a lunar eclipse coming up. All that and more. Thank you for listening. See the sky this week. I'll see you next week.